Okay, perfect. So as you've heard, I'm Raffaele Aaron Giampaolo, and PhD student with INFN in Politecnico di Torino. I'll be talking about the research I've done in the ARCADIA research group for fully depleted maps, which is basically an acronym for monolithic active pixel sensors. And in general, I'll be talking about some experimental campaigns and design that we've been carrying on here in Torino. So first of all, let's explain what the difference with normal electronics is and maps. Normal electronics usually have two different substrates. So you have to connect the electronics to the sensor, and this can be done through wire bondings, which is the standard version, let's say, while other versions are through bump bonding, which is small spheres which are interposed between the sensor and the electronics. And these are basically squished together in order to have a connection of the two. This is what you find normally in your laptops when connecting the GPU or CPU to the motherboard. And that's the reason why you cannot swap it and change for a new version. You have to buy a new laptop. The last but not so standard version of normal electronics and sensors is hybrid pixels, which use through silicon vias to connect the electronics to the sensor. So what this does is basically the two substrates are connected together, they're like attached, and some tunnels are basically etched out of the silicon, and conductive metal is put inside this tunnel to connect the two layers. And this is what you would find in smartphone cameras, basically. It's very interesting to talk about maps because differently from these previous kind of electronics that I've spoken about, we use one single wafer. So we do not have all the interconnections between the two substrates. We have a lower material budget, and we can have basically a higher signal-to-noise ratio for power dissipated. So basically what happens is that the whole sensor, the whole substrate acts as a sensor. And on the top surface of the wafer, we actually deposit all the electronics. And the electronics is then connected straight to the collecting electrodes on the surface, which are then obviously connected to the sensor. Where we see maps is mostly in consumer products, so camera phones and stuff like that, also which are pretty competitive with hybrid pixels because of their low cost. And what we will be seeing now and in the future is in high energy physics experiments, especially in particle colliders. The star detector already has particle colliders. It already has maps within it in the silicon vertex tracker. While in ALICE, we will see the Alpide chip is being assembled now with 10 square meters of maps. In the future, we will be seeing, on the other hand, medical treatment facilities for hadron therapy or radiotherapy, which will use silicon trackers based on maps to have a low material budget and thus having a very precise location measurement for the beams. Also on satellites, because obviously less interconnection makes the electronics much sturdier and so more space prone. Talking about fully depleted maps, on the other hand, we can see here the state-of-the-art technologies. They all have their pros and their cons, and mostly the most important ones are SOI, so silicon and insulator, HV-CMOS, high voltage CMOS, and the Alpide. So all these have, in this case, I'm showing the issues, which are, for example, for SOI, the box, which is a buried oxide, which basically brings to lower rad hardness because of the possibility of collecting charge just below the silicon oxide. In HV-CMOS, on the other hand, all the electronics is basically embedded within the electrode. So we have a p-type substrate with an N-well, which is basically the electrode. What happens here is that the big electrode implies a large capacitance, which is connected to the front-end electronics, and thus a higher power is needed for an equal signal-to-noise ratio. Last but not least, the Alpide. The Alpide is very, very interesting technology, but it does not reach full depletion. So with full depletion, what we have is drift collection, which is very, very important if you want to do timing. And Alpide has charge collection by diffusion. So when a particle crosses the pixel, some of the neighboring pixels might also be activated. The investigator high resistivity and the Malta chips are solving these issues, and by adding an n-type layer between the diode and the substrate. In our collaboration, the ARCADIA collaboration, we have something different. So what we do is we have an n-type substrate with an n epitaxial layer on top, and the P+ deposition is at the bottom. So what this does is it enables us to actually deplete the sensor from the back, imposing the high voltage required for the full depletion straight from the back. So on the top layer, we have all the electronics buried within a deep P well, which is then connected to the collecting electrodes. And this way, we can have low voltage CMOS electronics, which is designed with the standard CMOS process, basically, on the top. So we don't need some particular or exotic kind of CMOS processing here, but everything it can be done by any foundry, basically. Interesting here is that we can actually have drift charge collection because it's fully depleted. Also bulk rad hardness, and considering that we have a very small electrode, collecting electrode, we also have a high signal to noise ratio per power dissipated. In order to validate our electronics, we had to design pseudo matrices, which are basically arrays of pixels connected all in parallel. You can see here that we've designed two different thicknesses, electronics for two different thicknesses, and 3 different pixel pitches. To validate the sensors and the maps that we've designed, we had to do some electrical characterization and some irradiation tests with protons, lasers, and X-ray radiation. So you see here the pictures were actually done in Zagreb, in Croatia, where I've flown to do some proton irradiation tests, which were very interesting. And I'll be talking more about that in a second. For electrical characterization, we have to know where the full depletion voltage is. So what we do is we use IV curves, which are current voltage to current plots. And here you can see that when the current drops by a few orders of magnitude, and it basically steadies out, that's where the full depletion is. And at this voltage, our sensor is basically capable of reading out when a particle passes through the sensor. In these plots, you're seeing basically the irradiation test that we've done with protons in Zagreb. Here we've basically beamed 2 MeV protons straight onto our sensors. These are pseudo matrices. And in the left plot, the 3D plot done with MATLAB, you can see the metal lines, which are the darker areas. This plot is actually cut. So what you see on the right side are cuts of the left plot. And here you can see that there's a 2% loss over the metals, but very interestingly, there's a very uniform charge collection efficiency. And we published this on Transaction on Electron Devices some time ago. Our fully depleted MAPS prototype, the first one is MATISSE. And this uses 0.11 technology node electronics with 1.2 volts and a 50 micrometer pixel pitch with 24 by 24 pixels. At the bottom left, you see a block scheme of the electronics, which adopts global shutter acquisition and with correlated double sampling. On the top right, you see some images from a test setup, a laser setup that we're creating here in Torino, where we want to control micrometrically a laser beam to focus on our maps. At the bottom right, on the other hand, you see the irradiation test done with iron 55. and the two small peaks, X-ray peaks can be fully identified. And knowing the energy of these two peaks and the distance between them, we can actually validate the noise and electrons also of our electronics. The peak of our research and development is the ARCADIA main demonstrator, which is the new version that's been submitted. And this adopts a 25 micrometer pixel pitch with 512 by 512 pixels, which are digitized basically the signals into a hit map with a maximum hit rate of 100 megahertz per centimeter squared. The ARCADIA main demonstrator can work both in low and high power, so also aiming for the possibility in the future of being used also in spatial applications. Talking about spatial applications, I've worked on designing part of the Astra chip, which is the adaptable space strip readout ASIC, which will be available in two versions. One fully monolithic, which is on the right side, the Astra versione integrata, and you can see a layout of the chip. It actually adopts 32 columns of monolithic, instead of pixel sensors, obviously it's microstrip sensors, but it has a configurable gain and a configurable peaking time, which is very interesting. And we've also designed a version which is called the Astra 64, because it has the possibility of reading out 64 channels or 64 microstrips. And it's going to be compatible also with commercial microstrips. An expected output for our Astra chip, you can see right here. So the idea would be to mount it on satellites. On the left side, you see an example of silicon strip for the CMS experiment. So basically, you would have silicon strips, which are the sensors, which are connected to the Astra 64 chip. These would be then mounted onto silicon trackers inside a satellite. And once this silicon tracker is hit by a particle, by an incoming particle, then we would have a signal which is shaped, as you can see at in the bottom left here. This is the output at a shaper node, and then it would be read out. So it would be sent to an ADC, as you can see on the top right side. This is just an example of a differential signal, which has been simulated post layout in our of our chip. So concluding, we would like to say that our sensor technology and the first fully depleted maps have been thoroughly tested and verified. And a new version of the fully depleted maps has been submitted to the foundry, and experimental tests will begin as soon as we get back our silicon, basically, which will be about around mid-2021. In the same period, we will be submitting a new engineering run with more functionalities in our electronics. Thank you very much for your attention, and this is the ARCADIA and Astra family, which I'm very happy to be working with. If you have any questions.
Thank you, Raffaele, for your very interesting talk. Now it is time for some questions for you.
Sure.
Okay, the first one is, how do you run irradiation tests? Can you tell us more about how they are carried out?
Okay, so I have here a very simple schematic. I'll find it here. This, for example, is a laser test. This is done on the PSEUDO matrices. So what we do is we have to bias our electronics with what's called a bias T, which is basically a device that decouples the low frequency and the high frequency signals, voltage signals, obviously. So we bias the sensor, the top electrodes, and at the same time we can read them with a very fast amplifier. So what we do is we then have to connect the bottom plate of our sensor to a high voltage, and we irradiate it with either laser or proton beams. And as you can see here, these are some of the tests that we've done in Zagreb also, where with infrared, you have basically light that goes straight through the sensor, or red with red light, wavelength. On the other hand, you only have like the first 4 micrometers, which are sensible. So you can actually see also the PUL structures. And I hope I've answered the question.
Thank you, Raffaele. Now we have another question. Do you know on which type of space application your Astra chip will be employed?
Yes. So basically, here I haven't said it, and I should have. I'm sorry. So as you can see here, there's the herd detector, which will be locked into the Chinese space station, and we are collaborating with the Perugia INFN group on actually designing Astra for this application. We are hoping to actually have our chip on board the satellite, but you have to consider that a satellite like this takes many years of research and development, and to actually have the product ready and everything ready, it takes a long time. But this is what we're hoping to get our chip on.
Okay, perfect, Raffaele. Thank you. We do not have other questions, so thank you again for your talk.
Thank you.